Okay guys, year 11 method students, so this is our last video um, of sequences. Okay, so this video is about infinite geometric series. What do we mean by infinite geometric series? Okay, so the key words here, so we understand what do we mean by geometric, right? So the key word here is infinite. Infinite is the uh, we use this symbol to refer to infinite. Okay, that means the numbers can goes on forever and becomes um, infinitely big. All right, so when we talk about geometric series, we know that is from a geometric sequence. Okay, and when we have a geometric sequence, for example, 1 over 2, 1 over 4, 1 over 8. Okay, so for this one, what's the common ratio? We use the second term to divide by the first term. The common ratio 1/2. Okay, so when we add them, we could it becomes a um, infinite series. All right, so we know that for this one, if we are talking about S4, then we just add the first four of the sequences. Alright, so if that's Sn, like what we have learned before in the last video, we are going to add all the terms up to the nth term. But for S to infinity, that means we will add them forever. Okay, but you can't do it if the common ratio is not less than 1 and greater than -1. Okay, so that's a condition for you to do that sum to infinity, or what we call infinite series. Okay, the condition is here, so this is the crucial condition. Okay, you have to satisfy this condition before you can even write that infinite geometric series. Okay, otherwise it's just illegal. Alright, so let's see another sequence, which is 32 minus 16a minus 4. Okay, this time let's see what's the common ratio. We use the second term divided by the first term. It's -1/2. So how about -1/2? -1/2, is it still between -1 and 1? Yes. So that's why it's still legitimate to write as infinity all the terms are add together. Alright, and for the last one, okay, for this one, 2, 6, 18, 54. Alright, so for this one, R is 6 over 2 is 3. So that means the common ratio now is greater than 1. It's no longer between -1 and 1. Okay, so we say infinite series was S infinity, does not exist. You can't even write it. Alright? Okay, so that's the basic idea. The problem is, how could we find such sum? Because there's no end, so we don't know the ending. Okay, so I'm going to show you that there's a rule which can help us to do so. Okay, need to create a bit of room here. Oh, sorry about this. I forgot to leave some space for this part. Okay, so let's see. Okay, so here's the rule. Okay, is this rule look similar to you? Look familiar to you? Actually, it's quite similar to one we have just learned. If you still remember, we have geometric series formula. Okay, so let's say for the sum of first n term, sum or the sum of the first n terms. Okay, so we've learned that before. We use S n to denote that. If you still remember the formula, that's a formula like this. Okay, of course you could write that's r to the power n minus 1, but if you do that, your denominator must be r minus 1. If I use 1 minus r to the power n, in the denominator I write 1 minus r. Okay? Okay, so what happens here? Let's consider one particular term. Let's focus on r to the power n. Let's see what happens. Okay, given a value, if that r is between minus 1 and 1, then what happens to that n? Okay, so we will see that then r to the power n will become 0 when n tends to infinity. Okay, how this is possible? Let me give you some illustration. Let's say if we use 1/2, which is 0.5, as an example. Okay. Okay, so let's define a function like 0.5, which is 1/2. Of course, this number is between minus 1 and 1, right? Okay, and let's say the variable is at the exponential. Okay, let's say what happens when x becomes very big. So first, let's say x is 100. Oh, okay, so something happened. So oh, doesn't allow me to do so. Okay, let's try another one. Sorry about this. I don't know this until now. Okay, what happens? Why this is possible? Okay, so you see that number is really small. That's exponential times minus 31. Means that's so this number actually means this one. Okay, so that's really a very small number. Okay, so let's see what happens if I keep going back on that exponential. Okay, let's say I give it one more 0, becomes more and more smaller, right? So that exponential, remember, that 10 to the power. Okay, so how about, let's say I give it more 0. You see that? Okay, so that's exclamation mark means, okay, they can't, even the calculator can't give you an extra small number, it just give you 0. Alright, okay, so that's the reason when the power becomes really big and the base is a number between minus 1 and 1, then you will have an answer 0. That's why it's justified if we have r, which is between minus 1 and 1, and that's r to the power n 0. Okay, so that's what happens. So if I change the above formula by using s to infinity, that means what? That means that r to the power n becomes 0, and 1 minus 0, it becomes 1 minus 0, isn't it? Alright, so it becomes t over 1 over r, so sorry, t1. That's the reason we got this formula. So to memorize this formula, actually it's not that difficult. If you could you could remember that's the formula for the for the sum of the sum of the first n terms Sn. If you remember the formula for that, and you understand that Sr is between -1 and 1, then when n's become really big, r to pi n becomes 0. Okay, then when that number becomes 0, and that formula effectively will becomes the formula for our infinite sum. Right, so let's apply this fresh formula for our questions. Let me put this formula right here as a reference. Okay, so for the first one, let's say for the geometric sequence 1/2, 1/4, 1/8, calculate the infinite sum. So when you see infinite sum, that means sum to infinity, right? S infinity, okay, of all the terms. Okay, for this one first, you see this is a GS with common ratio 1/4 over 1/2 is 1/2, right? And of course, you might track that's 1/8 over 1/4, so also 1/2. Okay, and also our first term is 1/2. So what do we mean by s to infinity? That means 1/2, 1/4, 1/8 goes on forever. But we can't just add them forever, right? So we use a formula. We use 1/2 t1 minus 1 minus r, which is also half. Okay, so that will give you half divided by half, which is of course 1. Okay, so does this series have a physical meaning for us? Let's consider this. Okay, let's consider this. If I have a rod, the length of the rod is 1 meter. Okay, so I'm going to do this. First, I'm going to cut it half, 50% and 50%. It looks a half, right? Okay, so that's the first part, first cut. So for first cut, I got half meter, and then the next I'm going to cut half of the remaining rod. Okay, half of the remaining, that means here possibly looks like half, right? Okay, so let me show you that. Okay, so that's the half of the remaining half, so that would be half of the remaining half. Okay, right, and then I'm going to do another cut of the half of the remaining half. Okay, so that's 1/8. Okay, and then let's say we do it more. Okay, let's do this one. Okay, another half, which is 16 meter. Okay, and we move on, but we can't draw it smaller, right? So we move on. Okay, so let's say if we add all these cut pieces together, what's the length? So if you add all these cut pieces together, that means half plus 1/4 plus 1/8 plus 1/16 and so on. Of course, the infinite sum must be equals to 1 meter because the whole rod is of length 1 meter. So that's why when you get 1, that makes sense, right? For a geometric sense, right? Although we could never cut it into small, very very smaller pieces. We could never do it infinite number of times, but we understand the idea. That's what we call abstraction in math, right? Okay, so let's do another one, shall we? Okay, so let's say this time, okay, we got first 4. I'm going to give you some time. You try to write your answer, and let's track the answer. You just apply the formula, so it's very easy. Okay, let's see the answer, right? So that's 16 4 over 3. One thing to be careful is that this time the common ratio is a negative number. Okay, so when you 1 minus r, it's actually 1 minus 1/2, so it becomes plus. So that's the only thing you need to be careful. Alright. Of course, you need to check whether that's r is between -1 and 1. It is actually. Okay, so that's the first example. Let's move to second example. It's still simple familiar one, but for this one I think you need to read the question. An apple tree produced 28 kilograms for apple this year. It's known that the production of the tree each year will only be 80% of the previous year. Determine the total production of the tree for the rest of its lifetime, including this year. Okay, so you need to calculate the total weight of apples this tree can grow. Alright, okay, so think about whether this is a geometric sequence first. Okay, 80% of previous year. So every time you need to multiply that 80% to get the production for the next year. Alright, so for example, if my first year is 28 kilogram, then my second year will be 28 times, let's say 0.8 kilogram, and my third year would be 0.8 times another 0.8. Let's write this one. So it looks like a geometric sequence with first term 28, common ratio 0.8, but since that common ratio is between -1 and 1, so you could find the total production of the tree for the rest of its lifetime, including this year. Okay, so because every time it will be 0.8 times of the previous one, so the apple tree will get less and less apples, but theoretically it will always grow some apples in terms of its mass. Alright, because a number you times 0.8 will always be some positive constant there unless you allow that power goes to infinity. Alright, so in that case, total production for the rest of its lifetime, we shall use this one s to infinity. Okay, 28 plus 28 times 0.8 plus 28 times 0.8 square forever. Okay, so for this one, it's an infinite series, so we could use T1. If you still remember that formula, T1 over 1 minus R, right? So, okay, so that would be the answer. Of course, you need to give it a unit. So the total production will be 140 kilogram. Okay. Okay, so second example is about another student in our class. That's a joke, okay? So it's not about the students, about another Apple, but this time it's an Apple phone. Okay, Alba bought an Apple phone, and she found that each time she recharged the phone, the lasting time per charge of the battery will be 1% less than its previous charge. Okay, so we understand that if you got a new phone, the battery will last longer per charge. Okay, then after several years, or possibly not several years, after 1 or 2 years, you might find that you need to recharge the battery much frequent than before. Alright, that means the lasting time per charge is much lower when it's getting old, right? So 1% less than previous charge. Okay, the initial lasting time per charge of the phone was claimed to be 24 hours. So initially, okay, it's 24 hours. I think for Apple phone it's not that short, but I just, for the sake of simplicity, I put it like a number for our example, right? Calculate the total time of usage of the battery. So until the battery becomes flat, how much time could you use it? Could Albert use it? Alright, so let me give you some time. How about this? Alright, okay, so let's go back to see. There will be some surprise. You need to be very careful about this question. Okay, let's see the answer. Okay, so okay, the for some of you, I guess, I bet at least half of students will get it wrong. Okay, the common ratio is not 1% or 0.01. The common ratio should be 0.999. Why? Because that's 1% less. 1% less. It's not 1% of the previous charge. You won't buy a phone which, when you charge once, next time you got only 1% of the lasting time of the previous charge. That just sounds ridiculous, isn't it? Okay, so actually this 1% less. So that means it will be 99% of previous lasting time. Alright, so actually the sequence should look like 24 times 0.99, 24 times 0.99 square, and so the first term 24, common ratio 0.99, and okay, so sum to infinity. Okay, you got 2,400 hours. It makes sense, doesn't it? Okay, if you use 0.01 as your common ratio, then the answer would be 24.24 hours. That means you can only use once. Okay, so sometimes you need to look at the number, the answer you've got, and try to make sense of it. Okay, remember this question? Okay, you might see it in the future, possibly in the examination, right? Okay, so there's another way to see. There's another type of question which is called how to convert a recurring decimal number into equivalent fraction. Okay, so but you need to use proper infinite geometric series, so you need to use an infinite series. So you need to think about a sequence, a geometric sequence. When they are added up, they could represent that's that's recurring decimal. Okay, let's think about what do we mean by 0.5 dots. That dot means 5 is recurring, like this. So actually it goes to infinity, right? There are infinitely many 5. Okay, could we just write this one like this? What do you think? Okay, let me write one more. Could you see that if we write like this? How about the first four? When you just consider the first four, it becomes 0.5555, okay? And that goes on. So this one could actually represent that 0.5 recurring, right? Okay, let's see, do these numbers form a geometric sequence? Yes, because 0.05 divided by 0.5, 0.1. Okay, let's see. That's 0. Okay, so that's 0.05 divided by 0.5, 0.1, and that's the second term divided by first term. But let's track third term divided by second term is also 0.1, and you could see they have a common ratio. They have a common ratio which is 0.1. So this is a geometric sequence with common ratio 0.1 and the first term. Okay, so this one becomes the first term. The first one is 0.5, but could we do it by using infinite geometric series? Yes, because that's R 0.1, which is greater than -1 and smaller than 1, of course. So that's why we could apply a formula for geometric infinite geometric series. Okay, so that formula says the first term T1 divided by 1 minus the common ratio. The common ratio 0.1. Okay, so you got 0.5, 0.9, and this question could be in the paper 1. That means you can't use your calculator. So you need to know how to use your manual calculation to get the answer. Okay, so that means you have to apply the infinite geometric series. Okay, that's the first one. Okay, let's think about the second one. We got two dots. Sometimes it would be better if we just draw a bar over 24. That means 24 is recurring. Okay, 0 to 4 to 4. Last time there's only one digit, but this time you got two digits. Okay, think about this. How could we do it? Okay, so the way to do it is like you need to rewrite the whole series into what we call a infinite geometric series. You need to write the whole recurring pattern into a infinite geometric series, and then you need to find what's the T1, what's the common ratio. Okay, let me give you some time. I pause here. Okay, let me show you the answer. Okay, can you see that? Okay, so this time, because there are two recurrent digits, so you need to have double zero to replace the two digits, right? And also, due to you use double zero, that means the common ratio, when you use the second term divided by first term, it becomes 0.01. Last time it's only 0.1 because there's only one digit. If there are two digits, it's 0.01. If there are three digits, it becomes 0.001. Okay, then you could apply that infinite series formula. Okay, and you get 24 for 99. Then you still need to simplify that. Okay, alright. Okay, the last one could be quite challenging because it's not 3-digit recurring pattern. It's just 2-digit, but there's one in front of 2 digits. Okay, so let's think about how could we write this one. So the pattern looks like this. Okay, let me give you should give yourself some time to see if you can create what we call a infinite geometric series pattern. Okay, you need to think about how could you settle with that's 2 3 2 3. What's your first term? Okay, so this one could be tricky. Yeah, it's trickier than the last two. Okay, so anyway, I'm going to give you some time to give you kind. Okay, so here you are. Okay, so um, the most interesting part is that you need to separate that 0.1 from the rest of the number. Okay, because that 0.1 is not part of the recurring pattern. Okay, so you need to separate that non-recurring pattern with the recurring pattern. Okay, so 0.1 plus then the following pattern is recurring, so you could see I could rewrite that recurring pattern into an infinite geometric series, and the first term is not 0.1 because 0.1 is the first term for the whole expression, but it's not the first term for the infinite geometric series. For the infinite geometric series, the first term is 0.023, and you use that one, okay, and in your formula, and you will get the answer, right? Okay, so that there are a bit of fractions and common denominator, and then you need to do the simplification. Okay, so it will be a bit harsh for you if that happens in paper 1, but I'm not quite sure. Possibly the number will be easier, but you need to know this skill. Okay, so there are 3 questions we've done. Okay, the first one will be easiest. The second one is reasonably simple because you just use the same method but with 2 recurrent. The last one will be the most difficult one. Okay, so let's do some application one. Sometimes you might see some complex and familiar application. Okay, so here we got a pattern, a figure which you see there's a series of semicircles. So AXB will be the first semicircle, and BYC and ZD and D somehow E, that it just loops to infinity, right? So it can goes on and on to infinity. Alright, so how could we do this part? Find the arc length of semicircle AXB and BYC. Okay, can we find the arc length for this? Alright, of course, it won't be too difficult. Alright, so let me do it just next to the picture. It will be easier for you to see, right? Okay, so for this part, I would like to see that as arc length for AXB. Let's write as this one. Okay, so remember the answer must be in terms of pi. Forgot to highlight this. Okay, arc length. So you remember the arc length, that means part of the circumference, right? So that's semicircle. So we know pi times d would be our circumference, semicircle divided by 2. So for AXB is the largest semicircle, the diameter is 16 divided by 2, 8 pi cm. Okay, so how about BYC, another arc length? Again, we're going to use the same formula, but this time, because the diameter is BC, which is half of 16, so become 8 divided by 2, become 4 pi cm. Okay, so let's see. The biggest is 8 pi cm. The second biggest is 4 pi cm. Okay, do you see that they are decreasing? Okay, find the maximum length of spiral curve form. How can we find the maximum length? It just goes on forever. How can we find the maximum? yes, in this case, you need to consider if something goes on forever, you need to consider what? Infinite geometric series. Okay, so let's say that is what we call sum to infinity, and this time we're going to use 8 pi plus 4 pi. What would be the next? You might consider the next would be half of that 4 pi, that would be 2 pi. Okay, so you see that this one's reasonably a very obvious geometric sequence: 8 pi, 4 pi, 2 pi. And let's say this is a first term, and the common ratio, I just use 4 pi divided by 8 pi, second term divided by first term, half. Okay, so the common ratio is half. The first term is already known, so we could use this formula, sum to the infinity formula. Okay, so you know how to do it. Okay, 18 pi cm. Okay, I think that will be our answer, right? Okay, so that's it. Okay, so in the practice, you got plenty to do. Okay, got plenty to do. There are 14D, there are 14 questions, right? And you just try to do as many as possible. If you don't want to use a textbook, you just use one provided by me. Okay, I just got the answers next to the question. Okay, you might just use it. Okay, so if you've got any problem with videos, you might just ask me, sending me emails, or post your questions in the OneNotes. I know that OneNotes right now is kind of hopeless, but sometimes we still need to use it. And also send your homework to the homework folder. Okay, or if you really like this video, you might have some comments in the YouTube, so let everyone to see it. If you don't like it, say nothing. Alright, I don't need your honesty in my YouTube channel. Alright, okay, thanks for watching, and just do the homework. Okay, see you next time.